my screen. And اوكي طيب جي انش 200 January 27. Majid, please turn off your mic. Majid. Okay. 2021. Okay. So today we continue with probability rules. Where we will talk about the total probability rule. So we'll continue total probability rule. And Bayes theorem. And also, I hope we can do an introduction to random variables. Okay, so let's start. Let's start with the law of total probability. And to do that, we need to define something which is partitions. Partitions of the sample space. So what do we mean when we say I have a bunch of events that form a partition of the sample space? Let's see. So the events A1, A2, all the way to AN form a partition of sample space S if. So we have three conditions that should be fulfilled so that I can say that event A1, A2, up to AN, they form a partition of the sample space. The first condition is that A1, A2, all the way up to AN are mutually exclusive, which means AI intersects AJ equals P for I not equal to J. So the intersection of any two events is 0. This is the first condition. Second condition is when I take the union of all events, it will give me the sample space. So union of I equals 1 to N of AI, which means A1 union A2 union A3 all the way to AN. If I take the union, it should give me the sample space. And the third one is I do not have any trivial event, which means all events should have outcomes. So all events should have outcomes. Right. So what does this whole thing mean? It means very simply, if this is your sample space, and then I start slicing the sample space into, let's say, A1, A2, A3, A4, and A5. I will call those events partitions of the sample space. If and only if they are mutually exclusive. As you can see, I do not have any intersection between events here. They are all side by side. So the first one is correct. Second one, when I add all of them, as you can see, they all form S. So it's like this, you split the sample space into those events. And the third one, probability of A is greater than 0. So at least I have one outcome in each event. I might have more, of course, but at least you should have one outcome so that the probability of that event is non-zero, positive. And consequently, you can easily show that for any event A such that probability of A greater than 0, then A and A dash form a partition. It's always the case that any event with its complement form a partition. So if this is my A, what's the remaining? We know that the remaining is, this whole thing is A bar. So A and A bar, they form a partition. It's always the case. Of course, again, we assume at least A has one outcome. Right. Let's do some examples. Maybe one example, very simple example. If my sample space S is the set of integers, then A1 is set of even numbers and A2 is the set of odd numbers, then A1 and A2 form a partition of S. Right? Because when you take the union of the even numbers and odd numbers, you will get all integers. And then A1 and A2, they do not have any overlap. They add to the sample space and they have elements inside it. Okay, fine. Now, given this definition of partitions, given A1, A2, all the way to AN, form a partition. Then for any arbitrary event, B, we can write B as what? We can write B as A1 intersects B union A2 intersects B union all the way to AN intersects B, which can be written in a simpler way, I equals 1 to N of AI intersects P. So what does this mean? Again, anytime you have problem understanding some events, just plot it using Venn diagram. What I'm saying here is that if you have a partition for the sample space, something like this, let's say, and then you have an event B that's something like this. So this is B, and then this is whatever. This is A1, this is A2, this is A3, and this is A4. What I'm saying here is that you can express B as the intersection of B with A1 and the intersection of B with A2 and the intersection of B with A3 and the intersection of B with A4. So if you add those four parts, you get your event B type. So now if I have those events, I can express my probability of B as probability of A1 intersects B plus probability of A2 intersects B plus all the way plus probability of AN intersects P. So simply I can write this as summation from I equals 1 to N probability of AI intersects B. And now using conditional probability rule, you recall conditional probability rule, which is probability of A given B equals probability of A intersects B over probability of B. So if I use that, or probably I should have written it in let me say probability of B given A. Let me write it. So probability of B given A equals probability of A intersects B over probability of A, which means probability of A intersects B, you can write it always as probability of B given A times probability of A. So if I use this rule to write this intersection, so now I can write probability of B, I can write it as summation from I equals 1 to N, and now I can write probability of AI times probability of B given AI, which is the law of total probability. So you can always write the probability of an event B as the summation of probability of intersections, and then each intersection you can write it as probability of that partition of the sample space multiplied by the probability of B given that partition. Why is this important? It's important because of what we say Bayes theorem. Will be used in Bayes theorem. So let me state the theorem, and then I will solve a couple of examples to see why is this important. Majid, go ahead.
Doctor, I understood everything till the conditional theorem. Could you explain me only this one? Because maybe yesterday's class I didn't fully understand this. This probability of B over A is equal to probability of A intersection B divided by probability of A. Could you please explain only this line, please? Sorry.
Probability. This is the conditional probability rule that we took last time. This is the definition of conditional probability. We said the definition of conditional probability, if you have an event B conditioned on an event A, by definition, we did not derive this equation. We just took it as is. This is the rule of conditional probability. If I'm conditioning on an event A, this is equal to the intersection of event A and B divided by the probability of the event you are conditioning on. So there is nothing here to prove. This is a rule that we took last time, and we applied it to different scenario. And the theory behind it, as we said, we are resizing our sample space. Once you condition on another or a related event, you just resizing your sample space. You are limiting the options for any related event to happen. So we just use that definition in rewriting the intersection of A and B to be probability of B given A times probability of A, and then I substituted this back in the summation to get the total probability rule. So I did not do anything new today. Okay. So Bayes theorem builds on both conditional probability and total probability rule. How is that? From conditional probability, let me turn my mobile phone off. From conditional probability, we know that probability of AI given B is what? Probability of the intersection divided by the probability of the event that already happened. So this is, we know that A intersects B. Again, this is the conditional probability rule that we did last time. So now I will replace this using conditional probability again. And I will replace the denominator using the total probability rule.
Doctor, did you mention about this theorem last lecture?
Conditional probability, yes. Yes, we took it last lecture. Conditional probability.
Tamam.
Okay. So now I can write the intersection of AI with B, the numerator. I can write it as probability of AI times probability of B given AI. And for the denominator, from the rule that we just derived, I can write the denominator as summation from J equals 1 to N, probability of AJ, probability of B given AJ. And this is the Bayes theorem that very shortly. We'll see why it is important. As you can see, the first thing you probably should notice from Bayes' theorem is that it relates probability of AI given B with or to probability of B given AI, which is the opposite. And usually, this is, since we assume that AI happens, so this is the prior probability. We call this is prior probability. And this one is posterior probability. So what does all of this mean, you might ask? Let's see. I know there are a lot of equations here. Abdullah, go ahead before we do an example.
Doctor, actually, I didn't understand the red square, the law inside the red square. I didn't understand it.
There is nothing here to understand. It's just relating probability of A given B to probability of B given A. So
yeah,
you have two events.
But how did you convert the probability of B into the sum of probability AI, probability B over AI?
Because we said, assume that I have a partition like in here, and you can split B into summation of all the intersections, right? So B is just B intersects with A1, and B intersects with A2, plus B intersects with A3, plus B intersects with A4. Okay? So B is composed of different intersections. And then the intersection itself, I can express it as conditional probability from the rule of conditional probability, from this rule. Okay?
Clear, doctor. Thank you.
But let's put this in action. Let's give an example to see why is this really important. Example about lung disease and smoking. And I hope none of you smoke. But let's get this example to see. Okay. So I will write it down. So let's say a certain study in the US here, we do not have, or I did not search for a local one. A certain study states that, in the US, 7% of the population suffers from lung disease. Okay. So I have the whole population of the United States, 350 million, 7% of them. So 7% is almost 25, 26 millions. They suffer from lung disease. Right. Then 90% of those 7%, 90% of them are smokers. Okay, so I have, of those 25 million, 90%, 22 millions, or 22.5 millions, or 22.5 millions of those 25 million, they smoke. Okay? We know also that 25.3% of people without lung cancer, without lung disease, sorry, I keep saying lung cancer, I don't know why, are smokers. So we said 7% of the population, they have lung disease. The remaining 93% of the people, or the 320 million, the remaining 320 million, they do not have lung disease. Those remaining 320 millions, 25%, almost one quarter of them, they are smokers. So I have one quarter of 320 is like 80 million. 80 million, they don't have lung disease and they are smokers. ماشي? I'm just setting up the scenario. طيب. Now let's define the events. Let's define event A. Event A is a person with lung disease. So now if you go to the US and you pick someone randomly, what's the chances that this person will have a lung disease based on the information I gave you?
7%.
7%.
7%. So the probability is
0.07.
yes. Okay, fine. Second question, let's define another event, B, which is a person is a smoker. Do we have a direct number for probability of a smoker? Do you have it ready? No, we don't have it. So what do we have? We have two things. We have probability of B given A, which is the probability that out of those who have lung disease, what's the probability that a person is a smoker given that he or she has a lung disease?
0.9.
0.9, right.
0.09.
90%. And what's the probability that out of those who have lung disease, what's the chances that if you go to that pool and you pick one randomly, that person is a smoker?
75%? No, 25.3%.
No, we said 0.253.
Yeah.
Because 0.2, we said for those who do not have lung disease, if I isolate those, I put all those who do not have lung disease, and then I picked one randomly. The chances that that person is smoking is 0.253. Okay? Now, what will be of interest to us?
Doctor,
Yes?
small question, please. Sorry.
Sure.
This 25.3%, they are out of all the population, or they are out of all the people who have lung disease and are not
For
smoking
those who do not have lung disease.
and are smokers?
So, yes, out of those who do not have lung disease, the ratio of smokers among those is 25%.
So means in all the population, they calculated who are smoking and those who do not have lung disease.
Yes, so assume that I have 100 million people, okay? 100 million people, I have 7 million of them, they have lung disease. Okay? 93 million, they don't have lung disease. Assume I came to those 93 million who do not have lung disease, and then I'm saying 25% of those, they smoke, but they don't have lung disease. of the 93 million. Okay? Okay. So now what will be of interest to us? We are interested, anyone who smokes, you want to see. You don't want to wait until you have lung cancer and then to check if smoking or not smoking. Usually, those who smoke, they want to see what a lung disease based on this data, right? So we are interested in P of A given B. It's the opposite one. We have probability of B given A, but we are interested really in B of A given B, which is the probability that a smoker suffers from lung disease. So I know certain person is smoking. What's the chances that this person will have a lung disease? So this is probability of A given B. So if we go to Bayes' theorem, we write probability of A given B as probability of B given A times probability of A and probability of B, which you can expand again as we did the Bayes' theorem as probability of B given A to probability of A over probability of B given A times probability of A plus probability of B given A dash times probability of A dash. So now let's just fill the numbers. What's the probability of B given A?
Doctor, can you please say
0.9.
again what is the probability of B over represent what?
Which one?
The probability of B conditioned A.
Probability of B conditioned on A. Probability that among those who have lung disease, what's the probability that a person is a smoker? So if they gather those who have lung disease in a certain area and you pick one of them randomly, what's the chances that that person is a smoker?
Okay, thank you.
So this you can do easily, but the other one that usually is of interest to us. If we gather those who smokes, what will be the chance that some of them will have lung disease? That's what will be of interest. That's what we are calculating. So probability of B given A, we know it's 0.9. Probability of A, we know it's 0.07. Then probability of B given A is 0.9 times 0.07 plus, what's the probability of B given A bar or A dash is?
0.0253.
What's probability of A dash?
0.03.
0.03. No.
0.93.
0.93, right? Probability of A dash is just 1 minus probability of A. And we know probability of A is 0.07, then probability of A dash is 0.93. So if you calculate this, you will see that this is 0.211, which is not that bad, right?
21%.
21%. So the
it's low,
chances
no
that
problem.
if you smoke that you have a lung disease is 0.21%. So this means that if you gather all smokers in the population of this study, you gather all the smokers in one place and you pick one of them randomly and you check if he has a lung disease, the probability is just 21%. Okay? So this is a demonstration of how to use Bayes' theorem. The other example I will do I'll do another example, which is a very popular example. Probably some of you read about it or you know it, which is the Monty Hall problem. Monty Hall is a famous show. Apparently, I did not watch it, but this scenario, many hosts they use it, and the problem says that, like, show there are 3 doors. Okay, door number 1, door number 2. Anyone knows this problem? So this is door number 1.
Doctor, back in school they explained that. Back in school.
Yeah, so I'm reviewing some very basic stuff to you guys. Okay. So now one of the doors has a car behind it. So there is a car behind one door. Okay. So now the host asks you to pick one door randomly. Okay. So host asks to pick a door, and you pick number 1, for example. Still, we did not open the doors. So now the host opens door 2, and of course nothing behind door 2. That's why he chose it, and asks you the golden question. Do you want to stick to door 1, or you want to switch to door 3, sorry. Will that make a difference in your chances of winning the car? So now he opened door 2, so we know the car is either behind door 1 or behind door 3, and we want to calculate which door has higher probability to have the car behind it. So basically, we are interested in calculating those 2 probabilities. So we need.
Shouldn't they be equally probable?
That's the intuition, but as we see the calculations, we'll say different thing, and then we'll try to explain it. Come on, but let's see why is that. So before it was 33 chance for getting, and changes it, I think 50 or 60, something like that. Okay, so let's see. We need to calculate the following 2 probabilities here. So the first one is the probability that car is behind door 1, given that host opens door 2, right? This is the first probability. The second probability, no, car is behind door 3, given that the host opens door 2. So let's see, I will do first one in details, and then I will leave you with the second one. So that
Doctor,
because you want to, yes.
Sorry, just to re-clarify, there are 3 doors, okay, and one of them has a car behind them. He asked us to choose one door, and he will choose one door, and then he will open his door.
No, he will ask you to choose one door. You pick, for example, 1. So then he goes and open one of the doors that does not have the car behind it, either 2 or 3. We assumed here that he opened door 2, and then he will ask you, Do you want to stick to your choice of door 1, or you want to change your choice so that you pick door 3? And then he will go and open the door you chosen. If it has the car, you will get the car. If it doesn't, you lose. And we are trying to see what's the best decision that you should take. Should you stick to your door, or you should switch to the other door? Right. So let's see. Let's calculate probability of, let me start from the beginning. Probability of car behind 1, given that he opens 2. So let's call this event A and this event B. So we want to probability of A given B. Again, this is using Bayes' theorem. This will be probability of the opposite, host opens door 2, given that car behind door 1, divided by what? Divided by I equals 1 to 3. No, we'll follow the rule directly, that host opens door 2, given that car, 1 second, car behind door I times probability of car, 1 second, multiplied by probability of car behind door I. Yes, go ahead with the question. There is no stupid question in class. Yes.
So, Doctor, these formulas, they'll be given, right?
What?
This formula will be given, right? As in
No, in the exam, I always allow you to have a formula sheet. So in your formula sheet, you will have this for sure, the Bayes rule. You should have this in your...
our own formula sheet?
Yeah, you will have your own formula sheet, yes. To write on it whatever you want. Okay. So let's fill these probabilities. So again, we are calculating probability of car 1, given that he opens 2. So let's see. So what's the probability that... Oh, I missed one thing. I should have probability of car 1. Probability of car behind door 1. See, the rule here says probability of A given B is probability of B given A times probability of A. So probability of car. So what's the probability that the host will open door 2, given that the car is behind door 1? Imagine the scenario now. We are conditioning. We know that the car is behind door 1. So the host will open door 2 or door 3. What's the chances that he will open door 2? What's the chances that he will open door 3? Anyone?
50%.
Right?
Yeah.
He has two doors to open, and he knows, the host knows where the car is. So if the car is behind door 1, remember here we are conditioning on the fact that car is behind door 1, then the host, there's 50-50 chance. He can open 2 or he can open 3. So this is 1/2 times. What's the probability that, in general, the absolute probability that the car is behind door 1? In general, when we start, what's the probability that the car is behind door 1?
1/3.
1/3, right? Okay. Right. Let's go to the denominator. In the denominator, I have three conditional probabilities times probability of car behind door I. So the first one is, what's the probability that the host opens door 2, given that the car is behind door 1? This is just what we did. No, at the numerator. Right. Let's go to the second one, which is interesting. 1 second, I will come to you. What's the probability that host opens door 2 given that the car is behind door 2?
0.
Why 0?
Because if it was behind him, he wouldn't open it.
Yes. So if the car was behind door 2, the host will never open it. So 0 times whatever, 1/3. The last one, what's the probability that the host open doors 2 given that the car is behind door 3?
1/2.
1/2.
No. What options does he have?
1/3.
Assume
Doctor.
that. No. So assume, imagine the
It's a
situation.
whole, it's 1.
Yes. It's 1. Why it's 1? Imagine the situation. Here, you picked door 1. So door 1 now out of the picture. And the host, he knows that the car is behind door 3. What option he has?
2.
He can only open door 2. So in that scenario, this probability is 1. He cannot do anything else. Times the probability of the car is behind door 3, which is again 1/3. If you do this, this will be 1/3. So the probability that the car is behind door 1, given that he opens door 2, is just 1/3 of the time. If you calculate, I will not spend time, I know this is not that easy, and this is a famous math problems, and people still challenging it. But if you calculate probability of car behind door 3, given that he opens 2, you will find that it's 2/3. So the wise decision always switch. You do this yourself so that you make sure that you understand. If you don't understand this, that's okay. At least you need to understand the previous example. Abdullah, go ahead.
Doctor, I didn't understand how did you put the term, which is the probability of host opens door 2 over car behind door 1. I didn't understand how did you derive this?
Okay. You understand the scenario, right? The probability of the host opens door 2, given that the car is behind door 1. So the host knows where the car, right? You agree?
Yes.
That the
Yes.
host knows where. So if he knows that you picked the right door at the beginning, so he knows for sure that doors 2 and 3, they are empty. Right? Nothing behind them. So what's the chances that he will pick one of them? There is nothing to prefer. Door 2 and door 3 to him are the same. So what's the chances that he will pick one of them?
He will pick anyone.
Yeah, so نص ونص, 1/2 and 1/2. Right? So he can pick this or that. That's why I put 1/2 for this probability. Okay, I'm going to please start getting into your blackboard.
But doctor, for example, sorry for interrupting, but for example, if I picked the wrong door and he opened,
you can, you will calculate all combinations. Assume that you picked door 2 at the beginning. So the problem will ask you about what the probability that the car is behind door 2, given that he will open either 1 or 3. So just it will be just the same, exactly the same.
So, doctor, if we chose door 3 in the beginning, the probability will be 1/3, and for door 1 it will be 2/3.
Always switch. So if you open, Shababi, and just for the rest, if you are not interested in this, please go and check in your attendance. I started the attendance. But if at the beginning you picked door 3, and then he opened door 1, So your wise decision is switch to door 2 after he opens door 1. If you picked door 2 at the beginning and he opened door 3, switch to door 1. Always switch to the other door that was not open.
Doctor, logically it doesn't make sense, but I think by the numbers it does.
You know why? With numbers it does, and by intuition, if you think about it this way, there is always a chance that he did not pick the other door because it might have the car behind it. And the decision of the host is based on two things. It is based on where the car is. So there is always a chance, an extra chance, that he did not pick the other door because the car is behind it. He has two things drive his decision. Randomness, because the two doors, 50-50. But there's an additional information he knows, which might or might not be the reason not to open the other door.
I understand. There's more chances of the other door which he did open to have. I get your point. Yeah.
Yeah. So again, this is not an easy problem to. I've seen people proving it, getting the same results, but using what we call entropy. Entropy is in information theory. There is a measure for uncertainty, and they always come to this problem and they calculate how much information you have in the different decision, and they proved also that because also this information measure depends on the probabilities underlying the different assumptions that you might have. Anyhow, so do this again at your at home if you are interested. But what matters is, as I said, what we call posterior probability. Posterior probability is the probability afterhand, what we need to predict or what we need to will help us in taking actions, like the smoking and lung cancer. We are not interested in what's the probability if you already have a lung cancer. If you have lung cancer, regardless it came from smoking or non-smoking, it's not an issue. You're already sick. What would be the opposite one? Are you joining from two places? Yeah, Nasser. Make sure to turn one of them off.
دكتور
Yes.
انا ما قدرت اسجل حضور الموقع، قال لي عندي ايرور.
والله it's call ITS. Those
Me
will,
as well, doctor.
every time we have this issue. I don't know why. Most of the students they manage to do it. Some students either make sure if you are connecting from your phone, for example.
انا من الجامعه قاعد كونكت من اللابتوب دكتور.
I don't know. Just send an email.
Again.
Okay, send the email. Yeah, we will keep it in file. And if this consists, we'll see what to do.
Okay.
I don't take marks for absence. So make sure that if this repeats many times, let me know. Okay.
Okay.
Doctor, I have a general question.
Yes.
Not regarding to today's question, but will we see this kind of questions in the exams?
May or may not.
Because seriously, if we see this kind of question, I don't think anyone will manage to solve them.
No, just again, two things that are important. You need to be good in defining what's the event you are interested in. This is very key. And then apply the rule. Don't be smart. Don't act smart in the exam. Act smart in life, okay. Act smart in the class, okay. Don't act smart in the exam. Define your events correctly and follow the equations or the rules that you will have on your sheet. Okay? And you can solve, inshallah, any problem that I give you. Okay. Fine. Let's, in the remaining 20 minutes or so, start the next topic that will continue with us for a few weeks, which is the topic of random variables and how to deal with random variables and how to to describe them and how to use them to calculate probabilities. So what's a random variable? Very simply, a random variable and we say RV. And Amin, please turn off your mic. A random variable is simply a function that maps the sample space of a random experiment to the real line. So basically, random variable x is just a function that maps S sample space into R or part of it. Fine. So what does that mean? Again, let's do an example. Flip a coin twice. So your sample space is what? Your sample space is head, 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 tail, tail, head, tail, tail. Okay, a second, drink some water. Okay, so now you can, in math, we don't like to deal with head, head to head, tail. We like numbers, right? So we can define a random variable x such that I will map, for example, head, head, I will map it to 0, head, tail, I will map it to 1, tail, head, I will map it to 2, and tail, tail, I will map it to 3, so that it's easier to deal with. So now, instead of writing probability of head, head is, what's the probability of head, head?
0.25.
0.25.
Which is 1/4. Instead of writing that, you write what's the probability that x equals 0, and you say this is 1/4. What's the probability that x equals 3, and then again you say 1/4. So no longer we want to say the probability of HH or TH or HT and so on. Okay? Right. So we use capital letters to represent random variable, the name of the random variable. So X, Y, Z, capital letters to represent the name of the random variable. And we use small letters to represent specific values of the random variable. So in this case, like in the here also x, y, z, and so on. So in the above example, x, the small x can be what? Can be 0 or 1 or 2 or 3. And we write probability of my random variable x takes a small value x is what? With probability 1 over 4, x will be 0. With probability 1 over 4, x will be 1. With probability 1 over 4, x equals 2. And x equals 3. Very simple. You'll get used to it as we move on. We also talk about types of random variables. If the random variable takes discrete values, can be finite, or countably again, infinite, then it is a discrete random variable. If it deals with real line values in the real line from R, then it is continuous random variable. And as you will see, the first chapter that we'll deal with talks about discrete random variables. We'll talk generally about discrete random variables, and then we'll talk about specific random variables of interest to us, like the Poisson, the hypergeometric, the binomial, and so on. There are many discrete random variables. And then once we finish discrete random variables, we will move to continuous random variable. Okay. Then we move to the important topic of characterization of random variables. How do we characterize, or how do we describe random variables? And we learn 4 different ways of describing the random variables. The first one is probability mass function, small f of x. We then talk about cumulative distribution function, capital F of x, and we talk about the mean or expected value of a random variable, which we call mu, or expected value of x, and variance of a random variable, which is sigma squared. Also, we write it as expected value of x minus mu all squared. And we'll define each one of those, and we will see how we use them, or what do they mean. So let's start with the first one, which is probability mass function. Some people they write as BMF, and we said it's a small f of x. So what does it mean? This is just, by definition, f of x is the probability that my random variable x takes a specific value x, which means that f of x lists the probability that random variable x takes a specific value x. طيب شو يعني؟ Let's do example. Again, let's toss a coin. And we know that we'll have head and tail. Then I define a random variable. If it's tail, I will say 0. So this is my random variable x. So now, what is for x, for random variable x? What is f of 1? What's f of 0? F of 0, according to the definition, is the probability that x equals 0, which means in the back of your mind, probability of x equals 0 is the probability that I will get a tail, which is what?
1/2.
1/2. 1/2, right? And then I have f of 1 is probability that x equals 1, and which is 1/2. So you can think of f of x as a way to distribute the total probability of one possible outcomes. We can think of it this way. I have the total probability that I should have is 1. How is this one distributed between the x's? Then x, so in this case, specific example, x0 equals 1/2, and x1, x equals 1 is 1/2. Let's do another example. Let's say flip or toss a coin twice. So we have head, 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 tail, tail, head, tail, tail. And then I will define random variable y. Y is the number of heads that I get. So what's the range of x? What are the possible values of x? Sorry,
0,
what
1,
are
and
the
2.
possible values of y? Possible
0,
values
1,
of
and
y
2.
are 0, 1, and 2, right? So now, what's f of y? If you want to write f of y is, again, by definition, probability of y equals small y. So I have 3 possible values. I have probability of y equals 0. We have probability of y equals 1. And we have probability of y equals 2. What's the probability that y equals 1? Y equals 0?
1/4.
What's that? 1/4, right? So this is f of 0. What's the probability that y equals 1?
1/2.
1/2, because I can have head tail and tail head. So I have 2 outcomes. So f of 1 equals 1/2. And then for this one, I will call it f of 2, 1/4. Okay? And usually we plot the probability mass function. So I can plot it This is y. This is f of y. So now let's assume this is 0, this is 1, this is 2. So the value at 0 is 1 over 4. The value at 1 is 1 over 2. And the value at 2 is 1 over 4. So we call this the probability mass function. The way we distribute the power, the total probabilities among the different possible values of the random experiment. Let me, before we close, I write some straightforward properties of f of x. And very simply, f of x by definition is probability of x equals x. So, which means f of x is a probability. So if it's a probability, it should be positive. I cannot have a negative f of x. F of x is the probability that the random variable takes a specific value. So f of x is always positive. And the second important property, you should tell me about it. What happens if I add all values of f of x? What do I get?
1.
1. If I add all possible values of f of x, they should add to 1, because this is what I started with. I started with a total probability of 1, and then I distributed those probability in over the possible values of 1. Let me probably, I have 1 minute or so. You can think of other examples. For example, this random variable. Define your random variable. Number of coin flips until you get a head. Abdullah, go ahead.
Doctor, can we use this with the car example above, the previous example?
You can use what?
These properties.
Of course, any properties for sure. يعني probability. You have, for example, you have your random variable has two options, right? To switch or to stay. You have two options. So you can call the decision to stick to your door x equals 0, and the event that you switch the door x equals 1, and you calculate the probability of x equals 0. It's 1/3. Probability of x equals 1 is 2/3. They add to 1. 1/3 plus 2/3, they add to 1, and they are both positive. Yes. So you can, any random experiment, any random scenario, you can turn it into a random variable, call it x, y, z, whatever, and then instead of writing down what's the probability that I stick to my door, what's the chance that I win? This is x equals 1, for example, and the other probability is x equals 0 or 2. And it's up to you. This mapping between events and numbers is up to you.
The second property, how will it be satisfied if you use it with the car example?
Yes, because you have two options, to stick or to switch. One of them, it has probability of 1/3, and the other one is probability 2/3. So if you add them, 1/3 plus 2/3 is 1. Yes.
No. I mean, like, if we, for example, assume that x is the possibility that the car exists behind door 1. There are two steps to reach that decision. The first one is in the beginning, which is 1/3. The second time is whether to switch or not, which is 1/2, right?
That's why I'm saying, you have to define, the most important thing in this class is to define your event. You cannot say, and you cannot mix two experiments. You are at one point of time. What we calculated is at one point of time. Shabab, by the way, feel free to leave. Class time is over. So if you want to leave, you can just leave. I'm around if you have questions. So the first random experiment that we can describe, or what we solved, is he already opened the door, he already picked the door, and then the random experiment that we do has two outcomes. You stick to your door, you switch the door. This is the random experiment. And we calculate the probability of each one. طيب. If you talk about a different random experiment, I have 3 closed doors. The random experiment is the chances that the car is behind one of them. Yes, that one is, you have 3 outcomes, door 1, door 2, door 3. Probability of door 1 is 1/3, probability of door 2 is 1/3, probability of door 3 is 1/3. So you have to be careful in defining what's your random experiment that you are considering. Okay?
Okay, Doctor. Thank you.
Okay. Sure. Any other questions, Shabab?
Professor, what's the use of defining this?
Hmm?
What's the use of using variables?
What's the use of?
Using